students, we are going to see about Schrodinger and its contribution to quantum physics. Quantum physics. Quantum mechanics differ from classical physics in that energy, momentum, angular momentum, and other quantities of a bond system are restricted to discrete values quantization. Objects have characteristics of both particles and waves, wave-particle duality, and there are limits to how accurately the value of a physical quantity can be predicted prior to its measurement given a complete set of initial conditions, the certainty principle. Quantum mechanics arose gradually from theories to explain observation which could not be reconciled with classical physics, such as Max Planck's solution in 1900 to the black body radiation problems and the correspondence between energy and frequency. In Albert Einstein's 1905 papers, which explained the photoelectric effect, these early attempts to understand microscopic phenomena, not known as the old quantum theory, led to the full development of quantum mechanics in the mid-1920s by Niels Bohr, Erwin Schrodinger, Werner Heisenberg, Max Born, and others. The other theory is formulated in various specially developed mathematical formalism. In one of them, a mathematical entity called the wave function provides information in the form of probability amplitudes about what measurements of a particle's energy, momentum, and other physical properties may yield. About Schrodinger, quantum physics thus reveals a basic oneness of universe. Erwin Schrodinger, born August 12, 1887, Vienna, Austria, died January 4, 1961, Vienna, Austrian theoretical physicist who contributed to wave theory of matter and to other fundamentals of quantum mechanics. He shared the 1933 Nobel Prize for Physics with British physicist P.A.M. Dirac. Schrodinger entered the University of Vienna in 1906 and obtained his doctorate in 1910, upon which he accepted a research post at University's Second Physics Institute. There is a 6-month period in 1926 at the age of 39, a remarkably late age for original work by theoretical physicists. He produced the papers that gave the foundation of quantum wave mechanics. In those papers, he described his partial difference equation, that is a basic equation of quantum mechanics, and bears the same relation to the mechanics of the atom and Newton's equation of motion bear to planetary astronomy. The solution to Schrodinger's equation, unlike the solution to Newton's equation, are wave functions that can only be related to the probable occurrence of physical events. The definite and readily visualized sequence of events of the planetary orbits of Newton is, in quantum mechanics, replaced by the more abstract notion of probability. Contribution to quantum physics. Schrodinger's wave mechanics. Schrodinger expressed de Broglie hypothesis concerning the wave behavior of matter in a mechanical form that is adaptable to a variety of physical problems without additional arbitrary assumptions. According to classical mechanics, if a particle of m is subjected to a force such as the potential energy is V xyz at position xyz, then the sum of V xyz and the kinetic energy P 2 by 2m is equal to a consonant, the total energy E of a particle. Postulating a wave function xyz that varies with position, Schrodinger replaced P in the above energy equation with the differential operator that embodied the de Broglie relation. He then showed that satisfies the partial difference equation. This is the time-independent Schrodinger wave equation, which establishes quantum mechanics in a widely applicable form. In 1928, the English physicist Paul A.M. Dirac produced a wave equation for the electron and combined relativity with quantum mechanics. Schrodinger's wave equation does not satisfy the requirement of special theory of relativity because it is based on a non-realistic expression for the kinetic energy. Schrodinger replaced P in the above energy equation with a differential operator that embodied the de Broglie relation. He then ensured the satisfy the partial differential equation. This is the time-independent Schrodinger wave equation which established quantum mechanics in a widely applicable form. An important advantage of Schrodinger's theory is that no further or arbitrary quantum condition need be postulated. The square of wave function has a physical interpretation. Schrodinger originally supposed that the electron was spread out in the space and that is destiny. At point xyz was given by the value of at the point almost immediately Bond proposed what is now the accepted interpretation, namely the gives probability of finding the electron at xyz. The electron spin hypothesis not only provided an explanation for the observed magnetic moment but also accounted for many other effects in automatic spectroscopy, including the changes in spectral lines in the presence of magnetic fields, Zeeman effect doublet lines in alkali spectra, and fine structure closed doublets and triplets in the oxygen spectrum. The symmetry of the wave function for identical particles is closely related to spin of the particles in quantum field theory. See below. Quantum electrodynamics can be shown that particles with half integral spin 1 by 2, 3 by 2, etc. They are called fermions. After the Italian born physicist Enrico Fermi, particles with zero or integral spin, example mesons, photons, have symmetric wave function and are called bosons. After the Indian mathematician and physicist Satyendra Nath Bose, who first applied the ideas of symmetry to photons in 1924 to 25, he requirement of antisymmetric wave function for fermions leads to the fundamental result known as the exclusion principle, first proposed in 1925 by Austrian physicist Wolfgang Pauli. Two electrons in the same atom cannot have an identical set of values for the four quantum number n, l, m, 3. The Schrodinger equation cannot be solved precisely for atoms with more than one electron. The principle of calculation are well understood, but the problems are complicated by the number of particles and the variety of forces involved. These difficulties of approximation methods introduced by the English physicist Douglas or Hartree, the Russian physicist Vladimir Fock, and others in the 1920s and 1930s have achieved considerable success. Start by assuming that each electron moves independently in an average electric field because of the nucleus and the other electrons, that is, correlation between the position of the electrons are ignored. Each electron had its own wave function called an orbital. The overall wave function for all electrons in the atom satisfies the exclusion principle. Schrodinger proposed his time-independent equation to describe the stationary states. He also produced a time-dependent equation to describe how a system can change from one state to another. Energy E in Schrodinger equation with the time derivative operator, he generalized his wave equation to determine the time variation of wave function as well as its spatial variation. The time-dependent Schrodinger equation reads: He quantity I is the square root of -1. The function varies with time t as well as with position x, y, z. For the system with consonance, energy has the form exponential function, and the time-dependent Schrodinger equation reduces to the time-independent form. An atom may change spontaneously from one state to another state with less energy, emitting the difference in the energy as a photon with the frequency given by the Bohr relation. If electromagnetic radiation is applied to a set of atoms and the frequency and the radiation matches the energy difference between two stationary states, transitions can be stimulated. The selection rules for radiation relate to the angular momentum prosperities
of the stationary states, the absorbed or emitted photon has its own angular momentum, and the selection rules reflected by the observation of angular momentum between the atoms and the radiation. Thank you, friends.